Okay, so let's start back this well, maybe we should like review kind of the steps up to this point. Okay, so let me go back up to the top. We have a principal ideal domain, and we have an irreducible element. And we want and what did we do so far? We have our irreducible element P, and we have AB in the ideal, and we have to show that either A is in the ideal or B is in the ideal. We just started by looking at kind of the ideal generated by A and P. And one of the possibilities is that this is generated by P, and in that case, we get that A is in the ideal generated by P. Now we're looking at the other case, which comes from when we look at the ideal generated by A and P, it is generated by a unit, okay? And any ideal generated by a unit is equal to start. Okay, so we want to first, let's just remind ourselves, if we have a unit, the ideal generated by a unit is equal to the entire ring. Why is that? So since C is a unit, so you can solve C times U equals 1. And in particular, anything in R, so you have the equation R equals C times UR. Now anything that looks like C times something is in the ideal generated by C. That means that any R is in the ideal generated by C, so R equals C. Okay. So this tells you that now the ideal generated by C is equal to R. And now let's go back up to what is I. I is all the things like AR plus PS. So in particular, 1 can be written as AR plus PS. So we can write 1 is equal to A times R plus P times S. Oh, I think I used R already and S already. So instead, let me write A equals AX plus P times Y for some X and Y. Okay, and I want to use this to show that B is a multiple of P. Oh, this is like kind of a usual trick. We just multiply through by B. So we get B is equal to ABX plus PBY. And now A times B, we know that's a multiple of P. That was our original assumption, or that comes from the first step. We have that A times B equals RP. Okay, so this is a multiple of P. This is clearly a multiple of P. It's P times something. So let's rewrite everything. So AB is just P times R and plus PBY. In other words, it's P times RX plus BY. In other words, B is a multiple of P. That's the other conclusion we wanted to reach. We wanted to prove either A or B was in this ideal, and we have now done that. Okay. So P is prime. Okay, and that's the end of that proof. Okay, so now if we have an irreducible element, it generates a prime ideal. We also want to understand like, well, what we really want is to know that that's a maximal ideal. Okay, so we just have a final final proposition. Okay. Let R be a PID. Let P be a non-zero prime ideal. And P is maximal. So for this proof, we have to suppose that we have P is contained in J is contained in R, and we have to show that either J equals P or J equals R. Okay, and actually, if you go back through the proof that every irreducible element generates a prime ideal, we have actually already done this, but let's just see what happens. Okay, so I'm not going to put in as much details for this proposition for certain reasons, but let's just see what we should do. So step one would be to write that J is generated by an element A, or okay, since R is a PID. 2. Well, since J contains P, so and you can also write P is generated by P. Now, since P is contained in J, P is in J. 3. That means P equals A times B. Because J is all the multiples of A, P is an element of J, so P equals AB. Now, since we know that prime ideals are generated by irreducible elements in a PID, P is irreducible. So that means that A is a unit or B is a unit. If A is a unit, that means that the ideal generated by A is equal to R. So that means that J is equal to R. If B is a unit, well then P and A are both multiples of each other. So then A is equal to P times B inverse, which implies that J is equal to P. Okay, so in any case, you get J equals R or P, so therefore P is maximal. Okay. Okay. So now we know that if we have an irreducible polynomial, that gives us a maximal ideal, which allows us to construct the field. Okay. So now I just want to use the rest of the time today to talk about irreducible polynomials and the fields they give. Example. Okay. Let f of x be a polynomial with the degree of f equals 2 or 3. And f of x has no roots in k. Okay, what does that mean, no roots in k? It just means that f of alpha is not equal to 0 for all alpha in k. Then f of x is irreducible. Okay, and the proof is to write f as g times h. write f as g of x times h of x. Now the degree, if you take degrees of both sides, you see that the degree of f is, if the degree of f is 2, you have 2 is equal to the degree of g plus the degree of h. And it's either 1 plus 1, 0 plus 2, or 2 plus 0. If the degree of g or h is 0, that means that h or whichever one is a scalar, in other words, a unit. So that will establish that, you know, that's the thing you want. That means that f is prime. The only non-trivial thing that might happen is that when the degree of g and the degree of h are both 1, but if degree of g, degree of h are both 1, those both have roots. So in the case, if the degree of g equals 1, then g of x just looks like ax plus b. And so g of x has the root. So you see that g of negative b over a equals 0. Well, now, therefore, f of negative b over a equals 0. Therefore, f has a root. F has no roots. Well, this can't happen. Okay, so you see that if okay, so you see that having a root is kind of like equivalent to having a linear factor. Okay, so if f has no roots, it has no linear factors. And if it has no linear factors, because of its small degree, it is actually irreducible. And similarly, if degree of f is 3, you have 3 is the degree of g plus the degree of h. And that can be 3 plus 0, 2 plus 1, 1 plus 2, or 0 plus 3. Okay, and if it's 0 plus 3 or 3 plus 0, that's fine. The only problems are these two, right? Because if the degree of h is 0, that means that h is a scalar, so h is invertible. In other words, that would be fine with f being irreducible. The only problem is when the degree of h is 1 or something. But in that case, if the degree of h is 1, you find that h has a root, which implies that f has a root, and that's a contradiction. Okay, so you're able to eliminate both of these as well. Okay, so for things of small degree, you can have roots, or sorry, you can check that a polynomial is irreducible by just by checking if it has roots or not. Okay. So as an example, you know, another example, if you remember back to year 1, the square root of 2 is not a rational number. Well, therefore, x squared minus 2 is irreducible. Well, therefore, you get a polynomial, you can construct a field in which the square root of 2 exists by looking at the polynomial ring mod out by x squared minus 2. And then if you call alpha to just be the coset of x, this is an element of k. One thing you see is that alpha squared is the coset of x squared, which is just 2 plus x squared minus 2, the coset. But this term is in the coset, so this is just the same as 2. So in k, you have the equation that alpha squared equals 2. In other words, you've made up a field where the square root of 2 exists now because you had that x squared minus 2 is irreducible. Okay, and in fact, in k, all the elements of k looks like p plus alpha q, where p and q are rational. Okay. It's not always true that having no roots means that you're irreducible. For example, you can have a reducible polynomial that has no roots. You look at x to the fourth plus 4. This is a polynomial with rational coefficients that has no roots. Okay, sorry. Right, so we have no rational roots, but you can actually find a factorization. I hope I remember. I think it's something like x squared minus 2x plus 2. Then you have x squared plus 2 plus 2x. Let's see if that gives the right thing. You have minus 4x squared plus 4x squared. So you have no x squared terms. Then you have minus 4x plus 4x. You have no x's. And then you have x squared plus 2. So you have 2x cubed minus 2x cubed. You have no x cubed terms. So if you multiply it all out, you do get that. Okay. So you can have polynomials with no roots, yet the polynomial is reducible. Okay, so this trick only works for degree 2 and 3. Okay. I did want to do one more example. Okay. Let me do one more example and then that's it, I guess. Well, there's still this problem set on ring theory, which like this, but let's just try and let's work this as an example. Right, so let's take K. This is going to be the finite field with 3 elements. In other words, the integer is mod 3. We call the elements to just be 0, 1, and 2, but really these are cosets mod 3. So as an example, you have 2 squared is 4, but 4 is just 1 plus 3, and in F3, 3 equals 0. So that's equal to 1 in K. So 2 squared is 1 in K. Negative 1 is negative 1 plus 3, which is just 2. So the negative 1 is 2, the negative 2 is 1, and so on. Okay. So we have this field, but it only has 3 elements. Okay. But now, we can look at constructing a bigger field than K. And how do we do that? Well, we just look for an irreducible polynomial. So one way to do that is to look at, you see that if I square 1, I get 1. If I square 2, I get 1. So 2 is not a square in K. If I look at x squared minus 2. This is a polynomial with coefficients in this field, K of x. Okay. Notice, let's call this F. Notice, f of 0 is negative 2, which is 1. F of 1 is 1 squared minus 2, which is negative 1. F of 2, that's 4 minus 2, which is 2. Okay. Anyways, none of these are 0. Okay. My field only has 3 things, so it's easy to check if it has no roots. None of the 3 things are roots. Okay, so F has no roots in K. Okay, so therefore, F corresponds to, you can do the same construction. You get a maximal ideal corresponding to F. So you maybe like let L just be K of X modulo F, which is X squared minus 2. And then you let alpha to be the coset of X. This is an element of L. And notice, again, the same thing happens. Alpha squared is equal to 2 in L. Okay. So now L is a field. Actually, L is equal to the kind of like linear combinations of alpha. So we'll just call it like A plus B alpha, where A and B are in the finite field with 3 elements. Okay. And actually, if you, so there's 3 different choices for each of A and B. L has 9 elements. Okay. So if you had a problem with the fact that 2 is square mod 3, you can kind of fix your problem by looking at this field L. So now in L, 2 is really alpha squared, so it is now a square. Okay. And the ability to do that just comes from X squared minus 2 being irreducible. Okay, and that is really kind of all I wanted to do today. So let's stop there. Did anyone have any questions before we stop? Yes, assignment 5 is going to be just the last assignment. Like there was a way that we could have done, yeah, it was. There was a way that we could have gotten 7, but it would have just been, I think it was just going to turn out to be like too much pressure. So basically we're going to have like another, I'm going to give you guys more problems to work on, and you can ask, you can, you know, work through the problems and ask for help, and I can even mark them if you want, but there's nothing that's going to be due anymore. Okay. Yeah, okay. Okay, anything else? Okay, so kind of the next thing that you should be looking out from me would be like your coursework marks, your like your, not the final marks of the course because there's still the final exam, but I mean the final coursework marks. Okay, so as soon as I get those done, I'll put a post on my e-learning to let you know. Okay, but I guess that's it. So you know, it's not, maybe not the last time I see you, but it'll be the last time I see you on Zoom this semester. So anyways, thanks for coming all those times. I really do appreciate that. And you know, if you have any questions, just, you know, just email. I am still, yeah, this is actually the last class. I will have like kind of review videos, but at some point there was this decision to change April 9th to be the last day of classes. I kind of missed that announcement, but it happened, you know, so. Yeah, so I will be having review videos, but this will be our last meeting, over Zoom. Okay. Okay. Okay, well, I guess that's it. Okay, well, have a good weekend, everyone. I'll talk to you guys later, I guess. Bye.